Hello friends, welcome to our channel Brain Alive. In this video, we will discuss enhancement only MOSFET. As its name suggests, it works only in enhancement mode, means when voltage between gate and source is greater than 0, means when the voltage is less than 0 or equals to 0, it will not work. So it is called off MOSFET. Normally it is off. This is the on-chip diagram of eMOSFET. For its detailed construction, refer video lecture number 47. Roughly, it consists of a lightly doped p-type substrate in which heavily doped n regions are made for source and the drain. And over the entire surface, an insulating layer SiO2 layer is formed. And these are the aluminum contacts made for source, gate and drain. The basic difference between eMOSFET and depletion type MOSFET is that in eMOSFET there is no channel between the source and the drain. The substrates extend entirely up to the SiO2 layer. But in depletion type layer there is a channel. That's why it cannot operate when the voltage at the gate terminal is negative, as there is no channel. Now we'll see the working of eMOSFET. First, we will apply a positive voltage at the drain terminal through this battery VDD and ground the substrate terminal and the source terminal. First, assume the voltage at the gate terminal is 0, means no voltage is applied. In this case, this portion is like this, means no channel will be there. So, drain current will be 0. Now suppose we apply a positive voltage at the gate terminal. This positive voltage will positively charge this aluminum metal. This positive charge will attract negative charges from this SiO2 layer. So the charge separation take place. Now these positive charges will attract electrons, means negative charges from this substrate towards this SiO2 layer, and these charges will be collected near this layer. As we increase this voltage more, a number of electrons will be collected here. When there is sufficient number of electrons are collected here, a induced channel is formed. This induced channel is also called inversion layer. At this time, there is a flow of electron from source to drain, and this current ID increases. So increasing the positive value of the gate voltage means increasing the conductivity of this channel, or we can say the resistivity of this channel is reduced. Now we'll discuss the drain characteristics of this eMOSFET. If we apply some positive voltage between the drain and the source and keeps on increasing this positive voltage at the gate, the conductivity of this channel is increased, means the resistivity is decreased. So in this case, this device works as a resistor, or we can say the device works as a voltage controlled resistor. This condition is shown through this graph. If we apply some positive voltage between the drain and the source and keeps on increasing this VGS positive voltage, this region shows the ohmic region, means conductivity of the channel increases and the resistivity decreases. So this works as a resistor. So this is called ohmic region. Now we'll see the effect of increasing the voltage between the drain and the source, keeping this VGS constant. We know that this drain is positively biased. So this PN junction, P-type substrate, and this N region is reversed bias. As we keeps on increasing this voltage through this battery, the reverse biasing here is increased. So the depletion region near this drain terminal is increased. It is increased so much that it decreases the width of this channel. So the width of the channel is reduced so much that the pinch off occurs, means a less number of electrons, means a limited number of electrons can flow through this channel from the source to the drain. So the current ID becomes constant. Suppose we fix the gate voltage at plus 3 volt and increase this VDS. A condition is reached when the VDS is at point A, means voltage is VA, when the current becomes constant. At this point, the channel becomes constricted, means limited number of electrons can flow from this region to this region. So the current becomes constant due to the pinch off condition. The pinch off will not occur until this VDS is equals to VGS minus VTH. VTH is called the threshold voltage. This is the voltage between the gate and the source at which the channel is induced and the flow of electrons takes place from source to drain, and also the drain current starts flowing. At this condition, the pinch off will not occur. But if we go beyond this condition, means VDS is greater than this value, there will be pinch off and the current ID becomes constant. In this saturation region, the device is used as a constant current device. Now we will discuss the transfer characteristics of E-MOSFET. These are called transfer characteristics because this shows the relationship between the input gate voltage and the output drain current. The relationship is between input and output. So these are called transfer characteristics. These transfer characteristics is defined by this equation. This is equals to drain current ID equals to K square of VGS minus VTH. This VTH is the threshold voltage. Here in the graph we can see when the VGS equals to VTH means threshold voltage, the inversion layer is formed and the current start increasing. This IDSS is the drain current when VGS equals to 0. This is due to the minority charge carriers and also called leakage current or the reverse current. We can see here the drain current is controlled by the input gate voltage. These are the symbols for E-MOSFET. This is N-channel E-MOSFET. Here the arrowhead is going inside the device, and this is symbol for P-channel MOSFET. Here the arrowhead is going outside the device. If you like the video, please hit the like button and subscribe the channel. Thanks for watching the video.